Hey everybody. Today we're talking about Poisson processes. We're in a situation where we have identical but independent events occurring at random over a continuous interval. Typically we're thinking about time. For instance, we might be counting the number of raindrops that fall into a bucket over, say, 1 minute, incoming calls to a customer service line, accidents along a busy stretch of road. Each of those might occur according to a Poisson process. Now, if we have an actual Poisson process, three technical properties have to be satisfied. First of all, the number of occurrences in disjoint, that is to say not overlapping, subintervals, have to be independent of one another. So like in that call center example, the number of calls in the first hour is independent from the number of calls in the second. Secondly, the probability of exactly one occurrence in a sufficiently small subinterval of width, say, delta t, is approximately lambda delta t, for some constant lambda that we call the rate parameter. In words, this is saying that when you get down to small enough intervals, probabilities are proportionate to the widths of the intervals you're on. Finally, the probability of more than one occurrence in a sufficiently small subinterval, say of width delta t, is negligible. So fundamentally on each one of these tiny little subintervals, you either get 0 or 1 occurrences. Now in practice, these assumptions are never quite fully met, and so when people say Poisson process, a lot of times what they mean is approximate Poisson process. And fundamentally, we're in a situation where those assumptions from that previous slide are just reasonable simplifications for the real-world situation. For instance, if you're talking about accidents along a busy stretch of road, the accidents probably aren't independent of one another, because if you've got conditions in place that are conducive to accidents, probably you're going to have a higher number than if you don't have those conditions. So suppose we have a random variable x that's just counting the number of occurrences on a unit interval when we're looking at a Poisson process with rate parameter lambda. We can find the probability that x is 0, 1, 2, 3, etc. In theory, there's no upper bound on the number of occurrences that can happen. For instance, here's a probability histogram for a random variable x that is representing the number of occurrences in a Poisson process with rate parameter lambda equals 2.5. And you can see that the probabilities peak at around 2, and there's no upper bound on the values that x can take, but the probabilities become vanishingly small pretty quickly. Like by the time we get to 9 already, they're pretty close to 0. To find the probability mass function of a random variable like this, the number of occurrences in a unit interval under a Poisson process, we divide that interval into n equal pieces, and we take n large enough so that the properties of a Poisson process hold. By that I mean we've gotten our subintervals small enough so that the probability of an occurrence on any one of the subintervals is approximately lambda over n, so lambda times the width of that subinterval. And the probability of 2 occurrences on a single subinterval is 0. So looking back at the properties that are needed for a Poisson process, there's this idea that for sufficiently small subintervals, these two things are true. Here we're assuming that we've gotten past that sufficient barrier. Finally, as with any Poisson process, here we're assuming that occurrences on different subintervals are independent of one another. So we've now gotten into a situation where we have n identical and independent trials, each of which has exactly 2 possible outcomes. You either have an occurrence or you don't. So we have a binomial distribution with parameters n, the number of subintervals, and lambda over n, the probability of an occurrence on any one of those individual subintervals. So we can compute probabilities just using our regular old probability mass function for the binomial distribution. The probability of getting x successes in those n trials is n choose x times lambda over n to the x times 1 minus lambda over n to the n minus x. Now this is an approximation, but as n goes to infinity, that approximation gets better and better and eventually becomes exact in that limit. So fundamentally, we need to take this expression on the right and take a limit as n goes to infinity. We start by doing some algebraic simplifications, writing out n choose x in terms of factorials, factoring out the factors here that don't have any n's in there, so lambda to the x over x factorial, and then finally breaking up the 1 minus lambda over n to the n minus x into 2 pieces, using a rule of exponents. The n minus x exponent breaks down to an exponent of n, and then times another factor with an exponent of negative x. It turns out that each of the 3 factors inside that limit has a well-defined limit, So we can evaluate the limit that we're seeing here by taking the product of those individual limits. This slide shows those three individual limits. For the first one, n times n minus 1 times n minus 2, all the way down to n minus x plus 1 over n to the x, both the numerator and denominator have x factors. And so we can break up that limit as a product of x different things, n over n times n minus 1 over n, etc. The limit of any one of those is going to be 1, so the product of all of them has a limit of 1 as well. For the second one, the limit as n goes to infinity, 1 minus lambda over n to the n. That's just e to the lambda, and that's a well-known limit. It can also be used just as the definition of the exponential function. Finally, the limit of 1 minus lambda over n to the negative x is 1. X and lambda are just fixed constants here, so the only thing changing in that limit is n. Lambda over n is going to 0, so we're getting 1 to the negative x. 1 to some just rational number is going to be 1. Putting all of that together, we get the probability mass function for x. So, just plugging in the things we got on the previous slide. Lambda to the x over x factorial times 1 times e to the lambda times 1. That all simplifies down to lambda to the x times e to the lambda over x factorial. And this is the probability mass function of the Poisson distribution, which models the number of occurrences of independent and identical outcomes that occur according to a Poisson process. And the support of this random variable is just the numbers 0, 1, 2, 3, etc.